Hello everyone and welcome back to a new video in Introduction to the Finite Element Method video series. And in this video we're going to be talking about the energy approach and the development of beam equations. Now please notice that this video is going to be a little bit mathematics heavy, so I really highly recommend that you open the book and read the entire energy approach after watching this video so that you can grasp the different mathematics that are within this lecture. With that being said, let's dive into it. So sit back, relax, and enjoy the show. Okay, so assuming that I have a beam of length L, and the beam has, of course, a cross-sectional dimension of B for width and H for height. So this is B, and that's your H. Has a load Ty, and this load Ty is actually a surface load and not a linear load. I will explain what this is in a moment. It also has a moment M1 in the beginning, M2 at the end, P1 in the beginning, P2 in the end. Notice that the forces are being applied based on the positive axis sense of the finite element method. Of course, the v-axis here is also the y-axis, and the x-axis might not be seen. It's clipped, but this is the x-axis. Using the energy approach, a structure reaches stability when its potential energy is minimized. Of course, the potential energy here is basically the sum of the internal energy as well as the potential energy of the external forces. And there is some little things I want to quickly talk about here. A small volume element is basically dA multiplied by dx. dA is the cross-sectional area. Now, dA is always going to be BH if it's a prismatic beam, meaning if it is a rectangular beam. And which means that if you take a small piece of the length, if I take a small piece of the length dx, then this little piecelet is going to give you a small volume, which is called dV. That's the first thing I want to mention here. It might become important because when you try to study the book, you will understand why this becomes important. The second thing is a small area or a small surface area, ds he calls it. And this ds is basically a differential surface area, meaning that if you once again have this B and have this H, that's your B, that's your H, and you want to find this little differential area, this small area, the topside area, it will be dB multiplied by dx, and we need this area because Ty is being applied on that area. Like you usually have linear loads on beams, but Ty is actually here a surface load, meaning that if you have a beam like this, then Ty is actually being applied on the entire surface, on the entire width, which means that, well, our conventional linear load, Q, let me call it, is usually equal to Ty multiplied by the width if the width is constant, and it is. Now, with that being said, let's continue. The internal strain energy, which is U, is basically half sigma x epsilon x dV for each little piece. Now, this equation is from mechanics of material. It's called the strain energy, and I think I've derived this in this video series. If not, you should just Google strain energy, and you will see that the strain energy is basically half sigma x epsilon x. Of course, there is a dV because we are summing up, because we are finding the strain energy of a small volumetric element. Now, to find the total strain energy, which is basically total potential energy of the beam, you will have to find or sum up the entire potential strain energy on all the beam. Of course, you have volumetric elements, so you should triple integrate, which basically gives you this triple integration, half sigma x epsilon x dV. That's basically a cool way of saying I'm going to add them all up. Now, in the previous video, I think in the truss, we were able to take the area out of the equation. This time we cannot. We cannot take the area out of the equation because on a beam, under a force, you would have a bending moment. And the bending moment causes compression on some sides and tensile stresses on some sides. Like it would cause some compression stresses on one side and tensile stresses on the other side, meaning that the stress is a variable along the area even, and the strain is a variable along the area. And for a case of uniaxial bending, the stress and strain would be constant for the width. But in a case of biaxial bending, you would have a variability of the stress and the strain on every point. Like if you go in the length, there is a change in sigma and epsilon because moment changes. Like if you walk through the length of the beam, the strain energy changes because the moment changes. And if you walk through the cross section of the beam, the strain energy changes because the epsilon and subsequently the sigma is changing. Something that we should keep in mind. Now, the potential energy of the external forces, well, is their work, but in negative. The reason why it's negative work, because work is basically losing potential energy. Because if you have potential, what's potential energy? It's something's ability to do work. It is able to do work. Now, when it does work, you are losing potential energy. That's why I have a negative sign here. Notice that body forces, which were called XB, are neglected this time. And you have the surface force multiplied by the area. V here is the displacement down. You know that the force goes down. So it will make work for every movement for the point that goes down. So you have V here. Of course, the nodal forces will have their work, which is basically the nodal force multiplied by the deflection at the node. Notice there is a summation here because there exists only two discrete nodal forces. Also, the nodal moments will make work, but this time they get multiplied by phi, which is the rotation. Now remember what our objective is. Our objective, just to remind you, is to say, I want to minimize the potential energy pi p, the total. Now to minimize this, I need to differentiate it with respect to variables. What are my variables? My variables are the movement at the first node, and this should equal to 0. And another variable, which is the movement at the second node. This d is differential, and this d1y is the movement. Also, the potential energy with respect to the rotation at 1 should be 0. And the potential energy with respect to the rotation at node 2 should be 0. Now, in its current form, I can only do those integration for this and this, but I will fail to do the integration for this part because V is a deflection field, meaning it changes with the distance x. And also V is not basically d1y or d2y, so I cannot differentiate with respect to it. However, I know that V equals a function of d1y, d2y, phi 1 and phi 2. So my objective here that you will see during this video is going to be, I will try to find V as a function of the nodal displacements, plug it in, and do my integration work, my derivation work. Okay, so with that being said, putting this stuff all together, you see here the strain energy, you see here the surface load energy work in negative, and you see here the nodal force work. Of course, the strain here, once again, is not constant. The strain was constant in a truss because we assume that there is average stress and average strain on the truss. In a beam, the strain is not constant and depends on your y. Y here being, if you remember from mechanics of material, y being the distance from the neutral axis. So that's how you can find the strain. It's something about curvature and the distance of y. And with that being said, I once again have to find V with respect to d1y, d2y, phi 1, and phi 2. I need to do this because I want to differentiate pi p with respect to those things. So that's why I always try to switch into the nodal displacements. Also, the stiffness matrix connects the forces with the nodal displacements. So it stands to reason to try to shift everything with respect to nodal displacements. And we can do that by saying the deflection field is going to be the shape functions multiplied by the displacement. Now, the shape functions are something I explained before. In the case of the beam, I have 4 shape functions. Also, if you don't remember that, I explained the shape function under something called the interpolation functions or the mixing functions. So I hope you can remember that. Now, those shape functions are already given. We have talked about them in previous videos and how we derive them. And notice I need to find the second derivative of V, which means I can find the second derivative of the shape functions. Why? Because look, V equals N1 d1y plus N2 d2y, I think, plus N3 phi 1 plus N4 phi 2. Now, I'm not really sure about the sorting of those N's and D's, but it's okay. And now we want to basically derive this with respect to x 2 times. Now, d1y is obviously not something with respect to x, so it's a constant. d2y is a constant when we derive to x. Phi1 is a constant with respect to x. Phi2 is a constant with respect to x. But n1 and n2 and n3 and n4 are not constants with respect to x. Those mixing functions and shape functions are functions with respect to x. So when I want to derive this, I actually need only to derive the shape functions 2 times. Now I'm going to show you one example only because I don't want to dive into the mathematics, it's too deep. So let me show you how I get this, for example. To get this, I will take the shape function n1 and derive it 2 times with respect to x. So let's do this. First of all, I have 1 over L3 and I will keep it aside because it's just a constant. And now I will derive the first time, so it's going to be 2 multiplied by 3x squared minus 3 multiplied by 2x L plus 0. Now what happened here is, well, let me just put a multiplied here and a multiplied here. The derivation of x cubed is going to be 3x squared. Derivation of x squared is going to be 2x. Of course, the L remains. That's the first derivative. I need to derive it a second time. So deriving it a second time, it's going to be 1 over L3, open bracket, 2 multiplied by 3 multiplied by 2x minus 3 multiplied by 2 multiplied by L. The 0, of course, just fades from existence. What happened is the 2 is as it is, the 3 goes down as it is, and the xy becomes 2x. Now, if you want to simplify this, 3 multiplied by 2 multiplied by 3 gives you 12x, so that's the one. 3 multiplied by 2 multiplied by L gives you 6L. Of course, the L cube is outside. That's how you got those little things. Now, you need to derive every single one of those shape functions and get their corresponding values and put them in the matrix. Then, basically, this means that the strain, look at this equation, right? The strain equals negative y multiplied by the derivation. Now we just agreed that the derivation, epsilon x, is going to equal negative y multiplied by this whole mess, d, which is exactly what you see here. Now having those big things seems to be a mess, so we basically call this a B matrix in bracket of matrices. Now this B, as usual, is called the strain displacement matrix, some people like to call it. Because remember, we're going to try, it's very easy to forget your goal here. You want to try to evaluate triple integration half epsilon x sigma x. And we have, of course, our y because you have our pi p. And then later we want to derive pi p with respect to all 4 nodal displacements. So it stands to reason to try find epsilon x and sigma x in terms of the nodal displacements. Now epsilon x is done. We have found it in terms of nodal displacements, but I still need to find sigma x in terms of nodal displacements. That's easy because as far as I know, sigma equals E multiplied by epsilon for a one-dimensional line. And that's the case. So you can see sigma x equals d epsilon x, where d is the elastic modulus. That should be self-explanatory, which basically yields to this equation. Why is this equation like this? Because epsilon equals negative y multiplied by the displacement strain matrix and d. So if you cram in another material, which is your E capital, he calls it d here, you end up using this. Now, you see we have matrices, so pi p needs to be rewritten in matrix notation because we have matrices here. It's not just a number. Now, the book continues rambling on and on and on and on, but what I want to say is the following. You have a function for pi p now in matrix form. And if you see v, you know that you can replace v by using the shape functions n multiplied by d, the displacements. It's a good thing to do this because the displacements contain the nodal displacements, something you will try to differentiate with respect to. Of course, there is a d missing because the d of differentiation here is missing. So once you have your shape functions and once you have rewritten the entire pi p with respect to the 4 nodal displacements, you will have to do a huge mathematical task to derive the pi p with respect to each displacement alone. Now, I have done this for the trusses because it was still manageable to do so. So I tried to dive a little bit deeper in trusses, but when it comes to beams, if I want to do this by hand, it will take me like hours, and it might just lose your attention because just mathematics now. But at least we know the mathematics, right? So if you do this entire trick, you get this final equation, which is something called k equals ei and that stuff. Now, I know it from other equations to be b db transpose. Of course, because d is the elastic modulus and is constant, it gets thrown out, and that's why I have elastic modulus outside. Of course, he's telling you if you integrate your B matrix with respect to x, you get this equation. The B matrix, the B vector transpose with the B vector to get a huge matrix of symbols, and then you have to integrate the matrix of symbols from 0 to L to find the stiffness matrix. Now, this is a huge mathematics undertaking that you can try at home, but for me here, I will just tell you magically, by the magic of mathematics, you would get your stiffness matrix, something that you have seen before. So this is the energy approach of finding the stiffness matrix. Of course, you would think, okay, why are you explaining this? I mean, there is the direct stiffness matrix using simple structural analysis concepts. So why are we going down this deep rabbit hole? I'm going with you down this deep rabbit hole for the second time, because in the future elements, when we reach shells and isoparametric plates and so on, the only option that you have to find the stiffness matrix is to go through this crazy stuff. So it's kind of good to see 2 times this being explained before you reach the real thing or the real deal, where this crazy stuff is the only option you have in finding the local stiffness matrix. Well, and that's it. Thank you very much for watching. And of course, before I finish, I want to give a huge CEE-sized shout out to our dear channel members whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support helps me produce the videos that we do every week. Of course, feel free to join the ranks of the YouTube members via the membership button that you would see in the channel description or the description of this video. And for the support of my members, I'm of course thankful from the bottom of my heart. With that being said, I hope that you enjoyed the video and it was beneficial for you. And of course, if you have enjoyed the video, then please like, share, comment, and subscribe, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.